Welcome everyone to the next seminar on probability stochastic process from IME USP. Today we have with us Lucas Affonso. Lucas has his degree in physics. He is here in USP, and currently he's a PhD student from the Applied Mathematics department here in IME also, under the supervisor of Rodrigo Bissacot. So welcome, Lucas, to our probability seminar, and thank you very much for accepting the invitation.
Okay, yes, thank you, Aline, for the invitation. And today we will be talking about a contour approach to multidimensional long-range Ising models. This is a joint work with Rodrigo Bissacot, Eric and Satoshi Handa, and we will start by reviewing some basic settings of spinlet systems. We'll talk about a little bit about the previous work that was made on this subject. And after that, I will explain the idea behind the contour argument that we developed. So let's start. We will consider the lattice ZD in dimension bigger than 2. The state space will only have two possibilities of spins. And the type of models we study is the Ising type of models. As you can see, is defined by this Hamiltonian that you are seeing, this big expression, that are ferromagnetic. This meaning that the coupling constants Jxy are positive, they are symmetric, and this last condition about the sum, we call regularity. That means that at each point you can only see a finite amount of energy. So some examples, I think the most important examples about these models are the nearest neighbor Ising model. I think many of you already saw this model before. And the next model that we will be talking during the rest of this seminar will be the long-range Ising model with a polynomial decay. This distance is the L1 distance, and the decaying parameter alpha is bigger than d to ensure that the regularity condition is satisfied. So we will also study a modification of this model with spatially dependent magnetic field that was studied in this paper that you are seeing there by Bissacot, Cassandro, and Presutti. Where they studied the model, the nearest neighbor model with a decaying field. They studied the phase transition, and also they studied uniqueness. So the finite volume Gibbs measure is given by this expression, the probability of seeing a configuration that is given by this expression that you are seeing. And the set of all Gibbs measures is defined as the closure of the convex hull of the limit, the weak limit of the finite volume Gibbs measures. And we say that there is uniqueness if this set G beta has only one measure, and it has phase transition when it has more than one measure. For ferromagnetic Ising systems, as we will be talking about today, there are two main measures, most important measures that we work is the measure with a plus boundary condition and the measure with a minus boundary condition. Okay, so I want to discuss first heuristic argument for the phase transition, so you can understand how we show that we have indeed two measures at some regime of temperature. So first, consider let's say a toy model that is given by I will only consider this configuration that you are seeing in the screen that are given by only balls of plus spins inside a sea of minus spins. So configurations are very simple. You can only see balls of many different ranges of plus spins inside the minus spin configuration. And to show phase transition, we want to show that the measures that I showed you before, the plus and the minus boundary condition, should be different. So what you do is you study the magnetization at the site 0, and by this very elementary relation, you just need to control the probability of seeing +1 on the site 0 for a measure with minus boundary condition. You should do the same for the plus boundary condition, but now with the probability of seeing a minus in the 0. But the arguments are usually similar, so we only work with the minus boundary condition. So it's not difficult to see that in this restricted model, you only have r to the power d, r to the d possibilities for the 0 to be to have a plus spin, and that the energy of these configurations are greater than what you are seeing in this part right here. You have a boundary term that's given by the nearest neighbor interaction. You have a term that is responsible for the long range interaction. And since we are studying the decaying field, we also will have a minus term that will compete with the long range in order to destroy the phase transition. So for the argument to work, the long range part is given by this expression, as you are seeing. In order to the phase transition argument work, we need first to see that this quantity here is greater than 0. Whoa. A beautiful 0. So for balls, you can study the asymptotics of the long range energy, and you see different regimes depending on the decaying parameter. You can see that when you have alpha between d and d plus 1, the asymptotics is actually greater than the surface term. So, and as the decaying field we can control the decaying field as it's by this expression by simply comparing the exponents. You can guess that the right theorem to prove the phase transition is this one, and it's easier to explain it by the following graph. In this axis right here, we look alpha minus d, and in this axis here we see the decaying parameter of the decaying field. And what we proved is that in all the gray region here of the parameters, we have phase transition. In this dashed line here, we need to assume that h star, the constant h star, must be small. I forgot to mention this constant is positive for all the stock. This constant h star will be positive. So okay. The study of long-range systems started with Katz and Thomson in one dimension, where they conjectured that the dimension they conjectured that there should be a phase transition for long ranges in systems when the decaying parameter was between 1 and 2. And Dyson solved this problem almost entirely. He compared with the hierarchical model. And it was in 1982 that Fröhlich and Spencer solved the last case for the decaying alpha equals 2, a critical case, using a contour argument that was inspired by their previous work on systems with continuous spins in 2 dimensions. So there were many results on long range systems, but not using the contours. And after a very long time, there was this paper of Cassandro, Ferrari, Merola, and Presutti that extended the contour argument for all the other, for almost all the other region of decaying parameters, but they have to use an additional condition that the nearest neighbor interaction should be large. And it was with Littin in his thesis and Littin in Picot that they managed to extend the argument for all the region of the decaying parameters. But since his work was based on the previous work, he still have to assume that the nearest neighbor interaction was large. And it was recently, 3 years ago, there is this result of Bissacot, Endo, Vanetta, Kimura, and Russell, where they proved the phase transition for the nearest neighbor interaction being 1, and for alpha and for the decaying parameter, they still have a condition on the decaying parameter. So now for multidimensional models, the situation is a little bit different. We have this paper, this old paper by Genibre, Grossman, and Huel, where they improved. They have an enhanced Pyros argument, the usual Pyros argument, but allowing now long-range interactions. But they need to ask that the decaying parameter is bigger than d+1. And as you may remember, as we showed before, this regime alpha bigger than d+1 is special because the long range interaction behaves like a surface term. So at the end of the day, you should have a competition between the long range interaction and the short range one that is a surface term. So it's natural that these appear, but it's strange for ferromagnetic models because we should have a phase transition for all the region between d and d+1 also. And after that, we have a result by Park using now Pirogov's 9 theory. In this work, they have the Park managed to extend they have a contour argument. They extended Pirogov's 9 theory for different state spaces, finite state spaces. So in this work, he can study Potts model, the long-range Potts model, for instance. But now he has to make an even stronger requirement on the decaying parameter. It should be bigger than 3d+1. All these conditions are, as I said, strange for ferromagnetic models. So we decided to see to try to prove a contour phase transition using a contour argument for all the region of the parameters. So in the heuristic argument that I told you, the system is given by balls, so they are easy to do. But in the real, let's say in the real life, you have many different geometries. The distribution of the plus spins inside the minus spin may be messy, so you need an idea to arrange this this difference in a way that is useful to prove a phase transition. And this idea are the contours. So the first thing we need to talk about is the notion of correctness of a point. For a given configuration and a point in the lattice, you say that this point is plus or minus correct if for the configuration you have plus spin, and in all of its nearest neighbors you also have the same sign. So it's correct in this sense. It's correct because it equals the sign in a point is equal of it as its all nearest neighbors. And the boundary of the set are the set of all the points that are not correct, that we call these points incorrect. So in an example, as you see this configuration here, you can think that outside the left box you have all plus spins, okay? So let me show you. Like if you look at this spin right here, you see that all its nearest neighbors are minus. So this point is minus correct. And if you look, let me see, at this point, for instance, you may see that all its nearest neighbors are plus, so it must be plus correct. And for an example of a point that is incorrect, you can look at this point right here, and you may see that it has a nearest neighbor that has a different sign. So for now on, when you see in the images a gray region, you usually talk about the region as being a region of incorrect points. So the first thing in order to define the contours is that we need to define a proper partition of the boundary set. In the usual case, you usually just break the boundary set into connected components, and this is the usual contouring Pirogov scenario. But in long range, this is not sufficient because in long range systems, if you have large portions of the space that are not so distant, their interaction may be huge. So this is a problem for the contour argument. So we need to have a way to separate the sets properly in a way that the interaction between these parts are small. So first thing, we fix three real numbers, M, R, and A, positive real numbers. And for each configuration with a finite boundary set, we call this set gamma. Mri partition satisfying the following conditions. The first thing is that they must form a partition of the boundary, and they should satisfy this geometrical condition that each gamma prime should be contained in only one connected component of the complementary set of each other gamma. So what does this mean, right? So I will show you next a figure where this condition is violated. So as you may see in this figure, if I wanted to break the boundary set into gamma prime and gamma, as you are seeing now, the condition A will not be satisfied, because if you look for gamma and you look for the complement set gamma, you will be looking to this region here, this region here, this region here, and this region here. And as you may be seeing right now, gamma prime is not living in only one connected component of this these green things that I draw to you. So in order to this figure to satisfy condition A, you should break gamma prime into 3 more sets. Okay, so and then the next condition is a anti-fragmentation condition. It tells us that for all members of this partition, you can break the set into a finite amount of subsets, and this number n should be bounded by 2 to the r minus 1. Where the first thing is that they should give you all the gamma, the overlying gamma, and they should satisfy a rather technical condition on the distance. Okay, I will explain now what this means with an example, with 2 examples. Considering this picture, gamma and gamma prime as being the candidates for a Mri partition. We will work with m equals 1 and r equals 2. So this partition doesn't satisfy condition B2 because okay, I will also consider in this figure that all the sets have the same diameter. All these sets have the same diameter, equals to n. And in this case, if you try to break the gamma prime into subsets in order to verify this condition right here of the distance, for instance, you can break the set like this in three elements. You will see that all the elements of this family have diameter n. So in this condition of the distance, you should compare the minimum with n and n, because in this family gamma you only have one member, so this is trivial. N. And then the distance should be bigger. The distance should be bigger than n to the power a, and this is not the case that you are seeing right here. So this candidate as a Mri partition is not allowed. The right partition should be the trivial one. Should be everyone in the same set. So I have another example right here, where instead of the condition B2 being violated, we will have other kind of violation. You will have, in this case, now we consider that this set has the set here has diameter n squared, and all the other ones have diameter n as before. N, diameter n. And as you see here, you may try to break gamma prime as these 4 sets. And then in order to check the condition on the distance, you see that you have the minimum between n squared and n. It will be n, and to the power a, since m equals 1, and the distance between these sets is 2 to na. You might think that this would be allowed Mri partition. But the problem here is that in condition B, we have a maximum number that you may break your set. So you can only break your set in 2 to the power r minus 1. In this case, this number is 3. So in order to the condition B2 to be satisfied in this example, we had to break the set gamma prime into 4 components, and this is not allowed. So you have here more than one way to fix. You can, as before, just take everyone, or you may consider this set, and this set as a valid Mri partition. So continuing, we will use the Mri partition to construct the contours. And as I said before, you see that there is more than one partition, and you may be confused. You may be confused in order to what the question is, what partition should I take? Because if there is more than one partition, I must have a way to choose between them. And we always assume that we get the finest partition in the sense that it's contained in any other Mri partition, and this is unique. And I will give you now the idea of how to find a Mri partition. How to find a Mri partition that is not trivial. As you saw before in this example, you have the trivial partition. In this one, you have a non-trivial, but you may think that I was lucky because I made this example for today. But you may think, okay, but maybe you only have the trivial one or a useless one for most of the time. So what is the idea? The idea is like we will consider this boundary case, this boundary set, okay, with m equals 1 and r equals to 3. And in the first step, we will extract all the connected components that are too small. For instance, this component right here is what I call too small. So we extract them at in the 0th step. After that, we will cover the remaining set with cubes of side length 2. This is the first step, n equals to 1. And after that, we take the minimal cover with the cubes, and we will count how many cubes there are in each of these covers, but not only on the connected components. We must count the cubes that are, let's say, too close. In the first step, too close means that the distance should be less than 2 to the power a. In this step, close means the side length to the power a. That is fixed, okay? And after that, we count how many closed cubes there are. And if there are less than 2 to the power r minus 1, in this case, this number is 7. If there are less than 7 cubes, we extract them. We extract not only the cubes, but we will extract this region of the boundary set. And this is what will compose the sets of the Mri partition after we finish. So now we get this like this. And for the next step, we go to cubes with a side length a little bit bigger. Now this time we will look for cubes with side length 4. We look to the minimal cover. And now these cubes, in this step, we will look for cubes that are close, where the distance between them are less than 4 to the power a. In this drawing right here, I will consider that this is the case for these guys right here, and this is not the case for this distance right here. This is bigger than 4 to the power a. And after that, we count the number of cubes that are close. In this case, 7, and we extract this set. It may okay, and then you continue always doubling the side length that you used before. In this case, we use 8, and you may have some step where you still have too many cubes. It may happen if you have a large component like this one. So if this is the case, you just don't do nothing and go to the next step. And now this case, the cubes have side length 16. And you have 5 cubes, and now you will extract this region, and we will call it another member of the Mri partition. And in the end, the Mri partition will be this set, this one, this guy right here, this guy, and this guy right here. So you may have contours inside contours if they are too distant from the boundary. If this distance is too big, you may have a contour inside another contour. So our work was based on the notion of incorrectness points that are present in the work of Park. And in there, in order to define properly the contours, it's not sufficient to only have a geometric information. You should also have an information about the boundary. What I mean by that? Look at this picture right here. Since the gray region is the incorrect points, as we talked before, when you go outside the gray region, you are in a correct region. So in this region, all the spins should be equal. And in this case, you can color these transition regions here in the boundary between an incorrect region and a correct region with a color representing the sign of the correct region outside the set. And the problem with trying to determine a label now, a label is the color that you are seeing here. Is that since you can have many figures and many different transitions, you can have, as in gamma 1 right here, different labels for its boundary. Like in this one, you have a red. In this region here, you have a red boundary. In this here, you have a red boundary. This is also part of gamma 1. And in this region right here, you have a blue boundary. This is problematic because you need the label to define when two contours will be compatible or not. So you can solve the problem by looking to another thing that we call the volume of the contour, that you simply erase every hole that you find, and now you don't have problems anymore. You can only look for the label of the volume. You just erase the holes and look to the label and look the label of the boundary. So in this case here, the contour only have the set. Actually, the set only have one big connected component for the volume, but even the volume may have other connected components, and we call exterior a volume component. We call it exterior if it's not contained in any other in the volume of any other connected component, and it's just a nice fact that the exterior components always have the same label. So you can define the sign of the contours. And finally, we get the right object to study long-range Ising systems. You have an element of the Mri partition, and you have also the information of the color of the boundary in the volume, its labels. Okay, so we say that a contour is external if it's not contained in any other. This is easy to see, and we will consider the set E lambda as being the set of all the families that are compatible in the sense that it is realizable as a configuration. This means that there is a configuration such that if you do this construction that I explained to you, you get the family gamma as a Mri partition. All the contours are exterior, they have the same label, and most importantly, its volume is inside the box, the finite set lambda. And you may think now that you may have a problem with, let's say, the entropy of the contours. How many possibilities of the contours there are? Because in the usual Pyros argument, where the contours are connected, or even in Pirogovsky theory, where the contours are also connected, you have at the most an exponential number of, depending on the mass, you have exponential to the power of the mass possibilities for the contour at most. But now we are allowing that the contours may have different connected components. So it's a nice fact, a really nice fact, that this is not a problem for us, because the entropy is still exponentially bounded. The possibilities of the contours are still exponentially bounded. So now finally for the phase transition, we need to define a auxiliary measure. We will not work with the usual finite volume Gibbs measure, because since you work with incorrect points, if the sign changes too close to the boundary, the incorrect point will not be contained in the set. So in order to not have this pathology, the contours that are not contained in the box that you are studying, so we just restrict the Gibbs measure we just condition to the event that the sign on the inner boundary of the sets is always -1. This guarantees that the contours are always contained inside the lambda. This is a restricted partition function, a partition function that only depends on the family of contours. And we say omega gamma is the set of all the configurations that have gamma as one of its element, as a subset of its Mri partition. And we define this map that arrays a contour. As you may see, maybe it's not clear by this expression, but what we are doing is this map erases a region of incorrect points by putting everyone to be -1. And in the positive interior, that is more or less, you can see that is the region where the plus correct points live. You make a spin flip there. So what is plus correct becomes minus correct, and what is incorrect is still incorrect by the spin flip. So what this map does is just erase a contour, and we need to define this, let's say, generalized surface term that, in the risk argument, you used only balls, but since the contours may have different geometries, we must look for this term that depends on the energy of the inside of the set lambda and with the outside, the interaction of the inside with the outside. And then with all these definitions, we can prove that when you erase a contour, a fixed contour, gamma, and you compare the energies, you still have a surplus of energy that's it's proportional of gamma, and depends also of the interaction of the positive interior, the long range interaction of the positive interior. So this is, we may say that there is a form of quasi additivity that Littin saw that it was what is important to prove the phase transition for these models. You should prove some bound like this. And now, how much time do I have? Okay, I'll just continue. So finally,
sorry. Yeah, we start 2 minutes later, so you still have 15 minutes.
Okay, so now we give the sketch of the proof of the phase transition. As I said before, now you have to control the probability of seeing a plus 1 in the site 0. And it's easy to see that since you have a minus boundary condition and you are seeing a plus in the 0, so you should have a change in the sign. So it must 0 must be inside the volume of a contour. So this is less than the sum of the probabilities of all the contours. And now using this proposition right here, and with the modification of the decaying field, what you need to do is just to analyze this competition. But since we are not studying, again, since these are not balls, you should have a more refined control of the quantities, and we have it. It's given by these lemmas right there. And you just need to compare for the case with alpha between d and +1. You just use it's a straightforward application of the lemmas. You just compare the exponents or to evaluate the competition, and then you can manage to conclude that this is positive. And after that, after you prove that this quantity is positive, you get on a term only an exponential term depending on the size of the contour. And then it's the usual Paros argument. You can proceed as before. Okay, so thank you. I think this is all. Do you have any questions?
Anyone has any question or comment?
Maybe just point out that this construction that he showed with the cubes and etc. This is what people call multiscale analysis. And basically, we are very close to Fröhlich Spencer paper, actually. So actually, in the end of the day, the main inspiration is Fröhlich Spencer in multiscale analysis, but the incorrect point and the rest of the arguments is a combination of other papers. But this idea of construct the contours as the intersection of the cubes with the incorrect points is from Fröhlich Spencer. And Lucas, maybe you come back in the definition of contour just to point out the key point for us. Maybe it's not clear for people that is not aware about this. In the definition of contour, Lucas.
Okay. The Mri partition.
Yes. Yeah. Sorry. Yes. You see. Okay. Stop here. You see that there is this condition B, and this was our, let's say, main contribution on this part of the theory, because you see what we are saying. That's the following. You cannot have a big, let's say, a big group of small contours because in the end you have the number of these small parts that you will break the contours in the conditions B1 and B2. You see, you cannot see a lot of small different contours and consider each of these small guys as a contour itself. We are forbidden this. And in the beginning, it's not clear that, okay, but how do you guess? Because exactly when our first guess when we start the project it was just, okay, let's try to understand Fröhlich Spencer and apply. And we tried to do this, but it's not possible. Because this if you erase the condition B, you are lost. Because the calculations in the end and the entropy of the contours explodes that you cannot control the thing. So let's say our contribution essentially is that we were able to understand Fröhlich Spencer and multiscale argument, let's say, and inside of this part of the theory, we are able to say, okay, we can just avoid a big number of small contours, and the argument still work. That's why we are able to enter in this region of between D and D plus 1. This is completely new if you compare with the rest of the literature. I mean, before it is REL and 66, let's say. And the Park, but we use some ideas of Park, like incorrect points and so on. But let's say the contribution of Park is also in this direction of get a Potts model, for example. Park can deal with Potts model, and we did everything for Ising, okay, at least until now. So this was the big contribution of Lucas, let's say, for this point is exactly this. You can say the following. Okay, you have a lot of small contours. You don't consider them, and you just take all these small guys together as a contour itself, and play with in this sense, and you can finish the proof. Let's say it was not a guess a priori. If you try to do the argument directly, let's say why you don't just use Fröhlich Spencer? You can think, okay, it does not work. This is the message here. Our main contribution in this condition B, which say that you cannot have a big amount of small contour close each other. You cannot. If you have a lot of contours, the another contour should be very, 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 very far. This is the condition B2, let's say.
Nice. And what is your guarantee that you don't have these small contours in close to each other? Like, what is your condition which implies this?
Yeah, you remember when Lucas did the pictures, and he said, okay, they are very close. So you just pick up the guys that are close as a contour itself.
Yeah, no, this part I get. I mean, what is in your system which guarantees this B condition? I mean, I understood that you take all the small ones and consider as only one in some sense, right? You put everything together, but how do you know that this will work? I mean, cannot you have smalls and far away ones, or how I say that?
I didn't get you. Did you understand, Lucas?
What
I think
condition which guarantees that you don't have a lot of small ones and far away? You see what I mean? Because you need the small ones but close ones, right? In some sense.
yeah.
So how can you say, like, I mean, how do you know that actually you don't have a lot of many ones, small ones and far away from each other?
Yes, but Aline, you can have this. This will be the fact that you have two contours very far each other. Just you see, you have a lot of guys.
Yeah. If they are small and close, you put them together, and if are small and then you just
you separated them.
Yes.
Okay.
So you see, so you will satisfy B2 because the distance will be bigger.
Because of this distance, you have this. Yeah.
Yes.
Mm.
Okay, let's say in this way, the condition B2 is more or less expected. Another thing that Lucas, okay, actually, I also forgot. Let's suppose that you watch this talk of Lucas and try to read the Fröhlich Spencer. You try to do this. Maybe it will be difficult to understand. Okay, you have to you have to read the introduction, but what Lucas managed to prove is the following: there is a lot of exponents in these papers of Picot and of Cassandro, Presutti, and Merola, and also Fröhlich Spencer. And there, for example, for us, we have this exponent A. You see, for them, it's a number. So this was another big step that we did. They just fixed a fixed number. Let's say, I don't know, 3/2, if I well remember. Lucas can correct me. But in these papers, I think one of the papers of Fröhlich Spencer, they have an interval, right, Lucas? I think between 1 and 2. I don't remember which one of the papers.
Yes,
but
in the Fröhlich Spencer papers, the construction should be the R is equals to 1. In their case, and depending on the work, there is different choices for A. In the one-dimensional paper, for the long ranges in model, they choose 3/2, and for the Anderson localization paper, for instance, A can be any real number between 1 and 2.
So this was another, let's say, a very difficult step to, let's say, to guess that, okay, they have exponents, but let's put a parameter there and try to see. For them they have a fixed number. For us, is a parameter, and you combine everything to get the result at the end. So we have estimates for these numbers at the end. If you look let's say the main proposition in the paper is exactly the first one, when you prove that you always have the Mri partition, and so we have explicit bounds for this M, A, and R. So that's why we are able to win, let's say.
Yeah, exactly. There is a problem because when you fix these parameters A and R, you have the problem that this means that the contour argument will not work for all regions of the decaying parameters. So you should allow that your contour construction can depend on the interaction. So A actually depends on alpha and on the dimension. So if you have, and this makes sense, because if you have a small decaying parameter, this means close to D. This means that the interaction is stronger. So in order to the contours don't communicate, then they should be farther away. So So this is one of our contributions. You can just adjust the parameter A to your problem depending on your decaying parameter, on the force of your interaction.
Okay, so anyone has any other question or comment?
Can I make a question? It's I was thinking about the Fröhlich and Spencer paper, and there's this papers by Mri where he's somehow so refines the analysis of Fröhlich and Spencer to get some more precise results about the phase transition for the one-dimensional model. I was wondering whether you imagine that you can have some sort of refinements here, or I mean, I don't know. You may have not thought about that, but I mean, so I was just wondering whether you consider these refinements by Mri in your context.
Oh, okay.
You can answer, Lucas.
I think I can. Actually, in the original paper of Fröhlich Spencer, let me see. Here, they write that they will not consider if they are dealing with the finest partition or not. And this was made by Mri in the work that I think you cited. And we have also this proof is not in the version of the archive, will be in an updated version, but we also have a proof that the finest Mri partition is unique, and it's based on Mri. And also to consider a further study of these contours in the direction that Mri studied in his papers, and also in Mri and Newman. You should be able to. You must actually develop a cluster expansion for these contours in order to study. I think these papers he studied the decay of the correlation, right?
Yes, that's
yes.
right. Yeah, yes, one of them, I guess. Mri and Newman, yes.
Yes, and there he develops the besides this fact of the finest partition that we have, he also have a cluster expansion for the contours, and this we didn't study, but surely it's possible to use these contours.
Okay, thanks.
If we don't have any other question or comment, let's thank you, Lucas, again, please.
Okay, so now
obrigado aí, Aline, pela oportunidade para o Lucas.
Valeu, gente. Obrigado pela paciência, tá? Desculpa, o computador bugou tudo.
Não parei a gravação, gente. Espera aí que eu tô morrendo aqui.
Ficou meu obrigado, então, né?
Não, eu tô aqui morrendo, tava tudo pro YouTube. Depois eu corto o finalzinho.
Tá bom.
Obrigada, Lucas. Imagina, não consigo parar a gravação, gente. Não sei, o Google Meet tá cada dia pior. Eu não aguento mais essa vida.